Thanks for the introduction. I'm Lei Xue from the Hong Kong Polytechnic University. I'm very honored to present our paper, Malton Tools on Device Non-Invasive Mobile Malware Analysis for Art. This work is joined with Yaqingzhou, Qingchen, Xiapuruo from the Hong Kong Polytechnic University and Guofei Gu from the Texas A&M University. This figure illustrates the trend of Android malware. It is forecasted that there will be more than 7 million Android malware by the end of 2017. Also, we can find there was a malware found per 4.6 seconds in 2016. However, in the first quarter of 2017, a malware was found per 4.2 seconds. So Android malware tools that can help the security analysts efficiently analyze the Android malware and quickly detect malware are in urgent need. Currently, various Android malware analysis tools have been proposed. Most of them are implemented with the following patterns. First, most of them focus on monitoring the sensitive behaviors in a specific layer. For example, Box runs in Android framework layer. It monitors the sensitive behaviors through hooking special Android framework methods. Trace runs in system layer. It is implemented through injecting the target app by invoking the function ptrace. So it monitors the sensitive behaviors through tracking the invocations of system calls. Second, some of these tools are implemented based on Android emulators, such as DroidScope and CorpDroid. Both tools are implemented based on the Android emulator Qum. Third, there are also some tools that need to modify the implementations of the Android runtime or the compiling tools of Art. For example, Taint Propagation is implemented based on the modification of Android runtime DVM. Taint Art and Artist are implemented through modifying the compiling to DEX2OAT of Art runtime. When the direct bytecode of the target app are compiled into native code by DEX2OAT, then insert additional Taint Propagation instructions into the target app. Some of these tools need to modify the implementation of the target apps, such as Orson. It needs to repackage the target app to attach the app with user-level sandboxing and policy enforcement code. So at the same time, malware also adopt different mechanisms to evade detection and analysis by these tools. First, they can detect their running environment to evade the emulator-based analysis. When the malware find they are running in the Android emulator, they will stop to release the malicious payloads and conduct sensitive behaviors. Second, malware can also protect themselves from being debugged. For example, some malware will inject themselves by invoking the function ptrace, because a process can only be injected once. So when the malware has been injected by itself, then the debugging tools, depending on ptrace, cannot inject the target app for debugging. There are also some malware that adopt obfuscation and packing services from being analyzed and repackaged. In addition, the packaged malware could not be compiled into native code by DEX2OAT, so the analysis tools, depending on DEX2OAT, do not adapt to this malware either. So to resolve all these problems, we have proposed a novel Android malware analysis tool named Malton. It conducts on-device and non-invasive analysis for the at runtime. Next, I will introduce our work about Malton following these 5 aspects. First, I will use a motivating example to illustrate the major functions of Malton. When this malware starts, it first registers a message handler to handle the received short message. When a short message arrives, it gets its telephone number and checks whether this message is from the remote control. Note that it compares the hash values of the telephone numbers instead of comparing the strings of the hash values for checking. If the short message is from the remote control, it will pass the remote command in the content of the short message, and then invokes the method read SMS to process this command. There are 5 different commands can be processed by this malware, and the actions of these 5 commands are implemented by both Java code and native code. So during the analysis of this malware, because the malicious actions refer to both Java code and native code, Malton should be able to monitor the sensitive behaviors in multiple layers and identify the cross-layer information leakage. Second, because the malicious actions are triggered by different remote commands, so Malton should be able to expose all the malicious actions triggered by these remote commands efficiently. We employ concurrent execution to improve execution paths. But for this malware, the constraints generated by the telephone numbers include hash calculation, so they are too complex to be resolved for generating new import. As this status, Malton should be able to force the application to execute a special path when the desired import cannot be generated. Before introducing the details of Malton, I will give a short introduction about the new Android runtime art. This figure illustrates the Android runtime DVM. For an Android app, all its dynamic bytecode are stored in DEX files. When the app is installed into Android system, the DEX files are optimized into ODX files by DEXOpt. During the running of the app, its dynamic bytecode will be interpreted by the runtime DVM. Art becomes the default runtime from Android system 5. When the app is installed into the Android system running at runtime, its dynamic bytecode will be compiled into native code by DEXOAT. Then both its original dynamic bytecode and the compiled native code are stored in OAT files. When the app during the running of this app, its native code will execute in at runtime directly. For the methods that are not compiled into native code, their dynamic bytecode will be interpreted by the at runtime. The OAT file is a special ELF file. It is embedded with both the original DX files and the compiled native code. So we can pass the OAT file following its format to get the code regions of all the compiled Java methods. Then we can check the method invocations according to the execution of the compiled native code. Next, I will introduce the details of Malton. Given an Android app, Malton will run the app on a real device with at runtime to conduct cross-layer monitoring and information flow tracking. Because Malton is implemented based on the dynamic instrumentation framework Vagrant, so it does not need to modify the targeting app. During the running of the targeted app, It conducts 3 major analyses on it, that are multiple layer monitoring, information follow tracking, and path exploration. After each running, a trace log is generated. It contains the information include invoked framework method, runtime functions, system library functions, and system calls. The taint propagation details are also stored in the log file. Based on the analysis of this log file, Malton will provide comprehensive behaviors of the target app to the users. The information includes the cross-layer execution paths, cross-layer data flows, and some implementation features of the target app. The left figure illustrates the cross-layer architecture of Android system. The Android framework is implemented by Java code, and all its implementations are stored in the file bot.oat. Android runtime and system libraries are implemented by native code. In this paper, we do not consider the Android kernel. The left figure illustrates the architecture of Malton. It is comprised by 4 major components which run in different layers, that are Android framework layer, Android runtime layer, system layer, and instruction layer. Because Malton is implemented based on background, it translates all the native instructions into its IR statements for instrumentation. Malton only checks the simple behaviors in instruction layer. In Android framework layer, 3 major components are designed to collect different information. The OAT file parser is designed to parse OAT files. With it, we can get the beginning addresses of all the compiled Java methods and get the information about the methods, parameters, and results. Java method tracker is used to track the method invocations and returns. It checks the method invocations through comparing the target address of each jump instruction with the beginning addresses of the compiled Java methods. If the target address equals the beginning address of a method, then the method will be invoked. Meanwhile, Malton gets the method's return address from the register LR and pushes the return address into method call stack. It checks the method return through compiling the target address of jump instruction with the return address at the top of the method stack. If they are same, the last invoked method will return. Because in Android framework layer, the Java class instance are represented by Java object in memory. So we use Java object parser to get the real content of special Java class instance. Take the result of telephone name, manager, get device ID as an example. This method is used to read device ID, and the result is stored in a Java string instance. The Java string instance is represented by Java object. When this method returns, we can get the address. We can get address of the Java object in memory. Then we can pass the Java object to get the concrete value of the device ID. In Android runtime layer, 5 models are designed with different purpose. Because Android malware can dynamically load malicious native code into memory, Malton tracks the dynamically loaded native code through monitoring the native code loading behaviors. Malware can also dynamically load malicious Java code into Android runtime. Malton tracks the dynamically loaded Java code through monitoring the Java code loading behaviors. For an Android app, its Java code can invoke its native code through GNI interfaces. Malton tracks the native methods invoked by Java code through monitoring the GNI invocations. Except the normal Java method invocations, the Java methods can also be invoked by native code and Java code through GenAI reflection and Java reflection. So Malton tracks the Java methods invoked by both ways through monitoring Java reflection and GenAI reflection behaviors. Note that Malton tracks these behaviors through monitoring the invocations of the corresponding runtime functions. So Malton is easy to be extended to support the tracking of other new behaviors. In system layer, Malton tracks 4 types of behaviors with 4 models. By tracking network operations, Malton can monitor the information leakage through network and the remote commands received from network. By tracking file operations, Malton can monitor the access of personal file in the storage. Because malware usually dynamically releases its malicious payload into the storage and delete it after using. So Malton also monitors the dynamically released and deleted data through monitoring the file operations. Malware can also dynamically modify its malicious payloads in memory. So Malton monitors the dynamically modified memory data through monitoring the memory operations. By tracking the process operations, Malton can also find the protection behaviors of the target malware, such as the anti-emulator and anti-debugging behaviors. In instruction layer, Malton conducts 3 major tasks. First, it conducts taint propagation to track the cross-layer information leakage flow. Second, it conducts in-memory concurrent execution to explore execution paths. During concurrent execution, sometimes the constraints are too complex to be resolved for generating new import. So Malton can use the direct execution to explore special execution paths when there are no new import generated. Next, I will introduce the implementation details of these 3 tasks. Malton conducts taint propagation according to the logics of IR statements and R expressions. There are 9 IR statements and 11 R expressions that are related to taint propagation. Next, I will use an example to illustrate how the taint tags are propagated. In this example, there are 2 IR statements. The first IR statement is used to load a wheel from the memory ABCD1234 and then port this loaded wheel to the temporary T12. The second IR statement is used to get the calculated wheel of temporary T12 and then stores the wheel into the offset 8 of thread state. Thread state is used as a gesture registers in Vagrant. So when the first IR statement is executed, Malton gets the taint tags of the memory ABCD1234 and then propagates the taint tag to the temporary T12. When the second IR statement is executed, Malton gets the taint tag of the temporary T12 and then propagates the taint tag to the offset 8 in thread state. Malton employs the shadow memory, shadow temporaries, and the shadow thread state to maintain the taint information of the memory, temporaries, and thread state respectively. Malton uses concurrent execution to explore execution paths. Because mobile device has limited resources and concurrent execution requires considerable computational resource. So we designed the offloading mechanism to improve the efficiency of concurrent execution. Malton runs the target app in mobile device with concurrent execution, and then outputs the constraints to the desktop. Then we resolve the constraints on the desktop using this resolver and generate new imports. And the new imports will be pushed into the mobile device for exploring new execution paths. Next, I will use an example to illustrate how the execution paths are explored. In this example, there are 3 conditional branches. All of them depend on the import CMD. After first running, 3 constraints are generated. Through resolving these constraints, we can generate 3 new imports. Then we run the target app with these new imports iteratively. And each new import can explore a new execution path, CQ, QF, DF, and so on. We find sometimes the interested execution paths are just related to a specific code region. If we run the whole app to explore the execution paths, it can bring heavy overhead. So we design in-memory optimization to explore the efficiency of path exploration. With path exploration, Malton just needs to run the specified code region to explore the interested execution paths. For example, Malton runs this code region with the import CM first to explore the execution path of read SMS. At the end of this code region, it changes the return address to the beginning address of this code region. And then Malton runs this code region with the import CQ to explore a new execution path. And Malton will iteratively run this code region with different imports until all the execution paths are explored. In addition, sometimes the constraints are too complex to generate new import for exploring new execution paths. So Malton can also use direct execution to force an app execute a special execution path without import. For example, the constraint generated in this code region includes hash calculation, so we cannot resolve these constraints to generate new import. However, in the IR statements, the condition of this conditional branch is stored in the temporary T. So we can modify the concrete view of temporary T from true to false to force this app execute forward. We have designed different experiments to evaluate Malton. Because of the time limitation, I only introduce the important evaluation results here. For more evaluation results, you can refer to our paper. In this experiment, we compare Malton with CopDroid and DroidBox on discovering into operations using 512 malware samples. For the CopDroid, we download the analysis results of these malwares from its website. For DroidBox and Malton, we run the target malware with each two to generate analysis reports. The comparing results are shown in this table. From this table, we can find that for all the 8 different malicious behaviors, Malton detects more samples than the other tools. Take the phone call as an example. CopDroid finds 52 malware perform this behavior. DroidBox detects only 1 malware perform this behavior. And Malton discovers 59 malware that have this behavior. So from this result, we can find Malton can capture more sensitive behaviors thanks to its on-device and cross-layer inspection. In this experiment, we evaluate the path exploration of Malton. This malware performs different malicious actions according to the remote commands received through short message. We specified the short message processing function as a target code region and run Malton to explore the execution path. The exploration results are shown in this table. The first column represents the command, and the second column represents the corresponding malicious behaviors. From both columns, we can find that all the 14 different commands and their corresponding malicious actions have been successfully explored by Malton. In this experiment, we also evaluate the in-memory optimization through exploring each malicious action with and without in-memory optimization. Take the command df as an example. If we explore the malicious action with in-memory optimization, only 5,000 blocks are executed. But if we load the whole app to explore the malicious action, there will be more than 22 million blocks executed. So from the results, we can find Malton can explore paths effectively and efficiently because of the in-memory optimized concurrent execution. Next, I will make a short conclusion of our work. We have proposed and developed Malton. It is a novel on-device and non-invasive analysis tool for runtime. Malton can provide a comprehensive view of the Android malware behaviors through multiple layer tracking and path exploration. In future, we will automate the in-memory optimization and the recovery from crashes during direct execution. Thank you.
Anyone with questions, please step up to the microphones. Go ahead.
Nice talk. I have two questions on the path exploration slides. Can you go back to that slide? Yes. My first question is how often you need to use the direct execution?
How often?
Yes, because this seems like you break the condition and the false execution, then this may give you an invalid path. For example, it checks it validates the pointer, and you force execution to jump into the guarded condition. Then you might get some crash or something.
Yeah, it may be cause crash.
Yeah, so I'm wondering like how often you have to use the direct execution.
It depends on your apps. If your apps have a lot of complex calculations, such as hash calculation, it will bring more direct execution. So if your app is very simple, there is no complex calculation, then direct execution will not be used.
Okay. Another thing is I'm not sure if you're familiar with the blanket execution technique or macro execution. So could you comment like your technique with their technique? Because in my understanding, you want like a force execution to get more sensitive information more as possible. Then why not just force to execute every instruction in your program and collect the, let's say, system call or something? Why you want to preserve the original execution at a best effort?
I think I use direct execution just to explore the special execution path. So I think it is not often used.
So if I put it in this way, so what if you use the direct execution to explore all the code components? So would it be a bad thing, or you have still the similar test results?
I didn't evaluate it.
Yeah, okay. Thank you. Thank you. Yeah.
Last question of the session.
Hi, this is Lena from UBC. So I just have some quick question about your evaluations. I'm curious whether you have any data on the false positives and false negatives of your tool, and also like the code coverage of your your tool when analyze Android application.
The code coverage depends on if you use the concurrent execution. If you use concurrent execution, it will improve the code coverage. So such this evaluation, if I use concurrent execution, I will explore all the execution paths in this specified code region. If I don't use the concurrent execution, it can explore only one execution path.
Okay. And you have like the false positive and false negative data on your paper. Sorry, I forgot to check your paper before I ask a question.
I didn't evaluate the false positive in the paper.
Okay, and one more question about your evaluation sample. So you use like real world Android applications, right?
Yes, this is a real malware samples.
And you have access to to their source code, and you don't need to do reverse engineering work, or?
Can you repeat it?
So to analyze the app, do you have like access to the source code of all the malware Android application, or you need to do reverse engineering?
Yes.
Okay. Yeah. Okay.
I checked
Thanks.
through its source code.
Okay. Thank you.
Okay, thank you very much, everyone. Again, thanks to the speakers.